Hey everyone, welcome to Code Harmony. Today we are going to solve LeetCode problem number 3243, shortest distance after road addition queries. This is a graph-based problem and it will be very easy to understand with recursive thinking. Let's have a look on the problem statement. Here we will be given an integer n and a 2D integer array queries. Here n will represent the number of cities we have, and the cities are valued from 0 to n minus 1. Let's say in this case we are having 5 cities, so it will be from 0 to 4. We'll come to the queries array later. Before that, let me show you how the cities are represented. And they have given that this is the initial state the cities are connected. Every city I is connected to I plus 1. So this is how n equal to 5 are represented or connected initially. After that, the queries array come into picture, where queries array, every element in this 2D array is going to be an edge from city U to city V. Let's say in this case city 2 to city 4. So this is the initial representation. 0 is connected to 1, then 2, 3, 4 respectively. And now after the query 1 is connect 2 and 4. 2 and 4 are connected and they will be connected by a unidirectional edge from U to V, and it is also given in the constraints that for every query is always of length 2 and U is always less than V. The same thing, V is greater than U. Okay, so these queries will represent the road, and we have to return is minimum number of path from node 0 to node n minus 1 after each query. So here in this case, let's say we don't have the queries into picture. We have n equal to 5. We have 5 cities and cities are connected in this form. 0 is connected to 1, 1 to 2, 2 to 3, 3 to 4. And if I ask you, what is the length of the shortest path from city 0 to n minus 1? Here in this case, from city 0 to city n minus 1, what is the shortest path? There is only one path. 1, 2, 3, 4. The shortest path is going to be n minus 1, which is 4 in this case. But what is expected from us is that we need to return an answer array. An answer array is going to be of the size of queries, and ith value in the answer array is going to be the length of the shortest path after I query is executed. So in this case we have 3 queries. After first query we will be connecting node 2 to 4. If I connect node 2 to 4, what is the shortest path from node 0 to node n minus 1? What is that path? 1, 2 and 3. The path is 3. At the 0th, after the 0th query will be 3. Now in the second query, they are connecting city 2 to city 0 to city 2. If they have connected this, my city graph will look like this. And here, what is the shortest path from city 0 to n? This path. From 0 to 2, I will go from 2 to 4. So after second query, the path will become 2. And after the third query, in the third query, they are connecting city 0 to 4 directly. If it is directly connected, the minimum part or the shortest path is going to be 1. So this answer array we have to return from the problem statement, and these two values will be given to us, n equal to 5 and the queries array. And there is one more thing to notice is that U is always less than V. There is always an edge from smaller city to bigger city. Okay, if there is no edge from bigger city to smaller city, it means we can directly say that this graph is acyclic, and it is directed as well because every edge going from U to V, so we are going to call it directed acyclic graph. We do not need to keep track of any like infinite looping or cycle in that graph, so we'll directly jump on our approach. Now the problem statement is clear to us. We will have a look on the approach. Here this is our initial state of the graph, but we have to return is an array. this array ith value is going to be the ith shortest path from node or from city 0 to n minus 1 after ith query. So first of all, we'll consider this query into picture, and this query is from 2 to 4. This query is executed, and now we'll find the shortest path from city 0 to city n minus 1 in this directed acyclic graph. So nothing, the problem here will become, just forget about all the other queries. First query is executed, and now we just directly have 5 cities, and we have to find the shortest path from city 0 to city n minus 1 in this directed acyclic graph. And how do we find that? We are sure that we have to start from 0 city. So we are definitely going to start from 0 city, and from 0 city we will see how many cities we can go. As per the graph, we can only go to 1 city. So this one step I will take, and I will tell the first city that the first city tell me how many path length is from city 1 to city n minus 1. Okay. So what is my recursive thinking here is, I'm definitely going to start from city 0, but I will assume that I will call some kind of recursive function. This is my subproblem, and that was my bigger problem. Bigger problem was going from city 0 to n minus 1. What is one step smaller problem? That going from city 1 to city 4. I will tell the city 1, just city 1, please tell me what is the shortest path from your city to n minus 1 city. So this function is going to give me the value of the shortest path from city 1 to n minus 1. That path I will just directly add 1 because I need answer from 1. So 1 plus solution of subproblem is going to be my answer. You might wonder that there might be multiple neighbors to this 0th city. So for that, what we have to do is we need to keep track of some kind of adjacency list, because it's a graph problem, and one node can be connected to multiple nodes. So we definitely need a adjacency matrix here, or adjacency list here. And we already discussed that it is a directed acyclic graph. Why? Because every destination city is bigger than the starting city. So for that, I can take a list of integer to track my adjacency. If I prepare the adjacency of this node or this city traffic, cities are from 0 to 4, 0, 1, 2, 3. City 0 is connected to 1, 1 is connected to 2, and 2 is connected to 3 and 4, 3, 4, and 3 is connected to 4. 4 is not connected to any of the city. So this is my adjacency list. And what I can do is I can directly write recursion, that we are always starting from city 0. From city 0 to we will go to 1. From city 1 we will go to 2. From city 2 we will go to 3 and 4 respectively. And when we encounter the city n minus 1, we are going to capture the answer. We have our answer. Okay. And here in my recursive thinking, what I did is from node 0, I will take one step, and after that one step, remaining value will be coming from my solution call. So let's say in this case, I am calling from the third node. If I call from the third node, my solution function is going to be from node 4 to 4, what is the path length? That is 0. So that is going to be my edge case. So edge case is when the value of the city is equal to the n minus 1, we'll just returning 0. Okay, so if I try to write a, let's say, solution function for this, we are just assuming that we are solving the first query for now. And for every query, after every query, let's say when this query is executed, there is another node added to the graph. Then we have to make our DFS or recursive call again. So initially, I have my starting city. Let's take the number of cities as well, because we need to keep track of our edge cases. We'll just return from this solution function. And what this solution function will return? From node u to n minus 1 what is the shortest path length. Okay. Initially, what is the value of u? U is 0 initially. And what is going to be my terminating case? My terminating case will be when u is equal to n minus 1. It means I have reached the last city. So now I don't have to cover any path. So my further length of the path will become 0. Okay. So this is my edge case. And now let's say if I am not on the last edge, what I will do is I will go to all the neighbors of u, and for all the neighbors of u I can get from adjacency list. Let's say we are at 2. So when we are at 2, we will just go to 3 and 4. We'll just add one step to that path. I'm going to use a for each loop for every neighbor in the neighbors adjacency list. I will just make a call to my neighbor that from neighbor, let's say from 2 is having neighbor 3 and 4. From 3, what is the path to reach n minus 1? That I will add 1. So I will get path from 2 to 4. So this is the path from neighbor. And if I add 1, this is the path from current node u. So this is the path from node u. Let's say I'm having 3 neighbors. So every 3 neighbor is going to give me three path values. So I need to capture the shortest path length. So in this iteration, I will keep on track the minimum value. So minimum of this value and this path is going to be my minimum path. Minimum path I can capture in a variable, and in the end, after this loop, I will just return the minimum value. I hope this recursion is clear to you. In this recursion, what is the parameter we are taking? We are taking only one parameter, which is current node or current city. Current city is u, n is just to pass through the parameter and can be global here. So there is only one variable u. And what it is returning? It is returning the shortest path length from any node u to n minus 1. So at every step, it is going to initiate calls equal to the number of neighbors. But if we try to look on the adjacency list or in the graph, let's say after second query is executed, our graph will look like this. And there is 2 ways to coming to city 2. Let's say when we are coming from this way we are coming here, and I will ask 2 that how many minimum number of steps from your location, your city to the n-1 city. So 2 will give me the answer, which is 1. So 2 have already given me answer. But when I am coming from this path 0 to 1, 1 to 2, in this case I will also ask 2 that what is the shortest path length from city 2. So in that case 2 will again calculate the same subproblem and give me the result. So what we can say is, here the solution call from 2 n. This is getting overlapped. It means there are overlapping subproblems. And whenever we are having overlapping subproblems in our recursion, we will try to cache the call. And this call, there is only one variable solution, which is city number. City number is u. And city number will go from 0 to n minus 1. So from these values, these 0 to n minus values, we need to cache somewhere. And this we can cache in a integer array of size n. And what is the time complexity of this function? This solution function is going to get us the result from city 0 to n minus 1. And after, let's say after q queries, the number of nodes in the graph will become n plus q. So in that case, order of n plus q is going to be the time complexity of my solution function. But this solution function is being called q number of times, because in every query I will call this function q queries n plus q. Number of nodes, number of edges in the graph is going to be my time complexity. And what about the space complexity? For every query, I'm going to store the answer. And for every node, I'm also caching the value of this solution function. So space complexity is going to be order of n plus q. This is the time and space complexity of our function. Here, first of all, I need to prepare the adjacency list. And in that adjacency list, after every query, I will keep on adding or adding the edge in my adjacency, and I will call my solution function. Let's take the adjacency list globally so that we don't have to pass it through the function calls. List of integer. Along with that, I'm taking a dp array globally to pass it in the solution call. Let's also take the n globally. This dot n is equal to n, and what is adjacency is a new array list for I equal to 0, I less than n, I plus plus adjacency dot array new array list. Okay, now my adjacency list is prepared, and in my adjacency list initially there is an edge from every I to I plus 1. So this we have to add in the adjacency for I equal to node city 0 and till city I minus 2, because I minus 1 is not having any edge. I plus plus adjacency dot get adjacency of ith city and then add I plus 1. Okay, now my initial state is prepared. What I will do is I will add for every query. For every query in queries, I will add an edge in the adjacency. Adjacency dot get query 0, which is my u to v. I have the edge. Add v value, which is query 1. Okay, this is added, and for every query we require an answer. So the answer is going to be of size queries dot length. Once the edge is added, I will call my solution function, and solution function is going to give me the result from city 0 to n minus 1. So n I have taken globally, I'm not passing it in the function. So give me the shortest path length from city 0 to n minus 1. Okay, and this solution function is going to give me the answer, and this answer we can store here. Let me take I variable here, integer I, initially it was 0, and after each query call it will be incremented, and this is getting updated. But there is also one more thing to keep track, that what is going to be the value in this dp array. Dp array, let's try to fill it with -1. Arrays dot fill this dp with -1. Why I'm writing it here? Because before every solution call it should be a fresh dp array, otherwise there will be some mismatch. Now I have captured the answer and I can return directly from it. Now we just have to implement the solution function. That is going to be our main recursive function to get the shortest path length. Private integer solution integer starting node, which is current u. And what is my terminating case? When the edge is equal to n minus 1. If it is already on the n minus 1 city, what is the path length? From here it will return 0. Now we need to check for all the neighbors. For integer neighbor and adjacency dot get u, I will capture the minimum path from all of the neighboring paths. Int minimum is equal to what can be the maximum value? Maximum value can be n plus 1. It won't go beyond n plus 1. Minimum is equal to math dot minimum and the solution from neighbor. Now I want the solution from u city to n minus 1. You have a neighbor after one step, and from neighbor, if I get the answer, I will have to add 1 in that path. Solution from neighbor. Okay, so this is my minimum, and in the end I can return minimum. I have not written the dp here, so before returning, dp of current edge is going to be the minimum, and after the processing, this is my processing section. After the processing, we usually capture in our dp, and before the processing we see whether we have the need of doing the processing or not. And if dp of u is not equal to -1, if it is -1, it has not been captured. If it is not equal to -1, it's already been captured, so we can directly return it from dp of u. This is the implementation of our recursive function, and we are using dp. This is the dp. Okay, this dp also need to be initialized. Dp is going to be of size n. Here it should be n. Okay, so dp is initialized. Let's try to run over sample test cases. On the sample test cases it is working fine. Submitting the problem. Submitted successfully. I hope you understood the problem. Thank you guys. Bye bye.